I will start our meeting today to cover this example. We have a pre-stressed concrete beam section is shown blue. It's a rectangular cross section. The beam is 50 feet span. Pre-stressing tendons. We have how many tendons do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 tendons. The area of these tendons equal 1.836 for all of them. By the way, for your information, these tendons have diameter of 1/2 inch. The area of one tendon, I'm talking about the common tendons used in pre-stressing. So the area of one tendons equal 0.153 inch square. This area related to tendons with this diameter. So in this problem, we have 12 tendons. That means the total area for tendons will be 12 times 0.153. Your total area will be 1.836 inch square. So I gave you the total area for tendons in one time. But sometimes, this one is important, please pay attention. Sometimes, probably, I will give you, hey, the tendons used are 1 inch diameter. And I will give you this cross section. So how can I get the final area for the tendons? You need to remember, for 1/2 diameter, the area of one tendon equal 0.153. Guys, it's wrong. It's wrong to say the area of one tendon equal by divide 4 times this diameter square. If you did this, you will get a different number. You will get 0.196. It's wrong because we have a table. We have a table based on the diameter. I can figure out the area of one tendon. Probably I didn't give you this table, but I'm giving you this information. Okay, so the area of one tendon with the diameter 1/2 inch is 0.153 inch square. You need to multiply this area by the number of tendons. You can get the final area. Okay, the ultimate stress equal to 170. The initial pre-stress 175. Are located as shown in the figure. We need to calculate the flexural stresses on the top and bottom fiber of the cross section due to a combination of pre-stress force and the unweight of the beam only. Guys, just to remind you, to calculate stresses, we need two things. The first one, effect of external load. We have a beam. We have uniform distributed load, probably dead load plus live load. This will give you a moment. This moment maximum equal WL squared divide 8. The second one, we have this cross section with pre-stress force, which has F That means we have eccentricity E, so we have to effect of F divide area and F time E time Y divide inertia. Do you remember that? For this one, we have stress equal M time Y divide I, or sometimes M divide S. So we have stress here, we have stress here, we have stress here. We need to add them together to get the final stress. So let's start with the first one. Effect of external load. The problem did not give you any live load, and also the problem asked you to get the final stress due to the effect of unweight of the beam. So this beam is simply supported with total span equal 50 feet. We have uniform distributed load here equal dead load only. And the dead load in this problem equal the unweight of the beam only. Do you remember how can we calculate the unweight of a beam? Yes, I can. 18 divide 12 time 36 divide 12 time 1. I'm assuming unit length, 1 feet, time gamma concrete, which is 150. Guys, I divided this B by 12 to be in feet. 36 divided by 12 to be in feet. 1 feet is a unit length of this beam. So, and the gamma concrete 150 pound per cubic feet. So 18 divided 12 time 36 divided 12 time 150 equal 675 pound per foot. So the bending moment due to the effect of this unweight will be a parabola. M maximum equal WL square divide 8. W 675, L square 50 feet square divide 8. This number will be 210,937 pound foot. Please make sure your units are consistent. That's fine. Any questions so far? Looks good? Any questions so far? Okay, so please read the problem carefully, because in the exam, you don't need to ask a question. The problem did not mention anything related to live load. Okay, we don't have live load. And also the problem mentioned we need to calculate the flexural stress due to the effect of unweight of the beam. So that's fine. We have unweight only. Okay. Second part, we need to talk a little bit about the pre-stressing force. But before starting, I need to ask a question. Anybody can tell me what is the eccentricity for these tendons? Just to remind you, the cross section has a centroid and the tendons has a centroid. The distance between the centroid of the cross section and the centroid of the tendons called eccentricity, E. Can you tell me what is the value of E? I need answer. I need someone to answer my question. What is the eccentricity E? Anybody can answer my question? So please locate the centroid of the tendons and locate the centroid of the rectangular cross section and tell me what is the distance between both of them. Yes, perfect rectangle. Why? Because we don't have tension. We don't have tension. We don't have cracks. So the whole cross section is working. Alan, I didn't catch your question. Will there be two? No, no, Cody. Brock, your answer is wrong. 18 is wrong. It's not the eccentricity. Cody, it's not 15.5. No. Guys, it's very easy. Just put a point at the centroid of the tendons and a point at the centroid of the rectangle. And then what is the distance between the 2 points? Yes, we have 2 rows. And we have 2 rows. Then the centroid of these tendons will be at this location, which is at a vertical distance from the bottom equal 4 inch. 3 plus 1. And the centroid of the rectangular cross section at half distance of 36. So the vertical distance between the centroid and the bottom is 18 inch. 36 divided 2. So the distance between the centroid of the tendons and the centroid of the cross section will be 18 minus 4 equal 14 inch. That makes sense? That makes sense? It's very easy. I told you, put a point at the centroid of the cross section. It's a rectangular with 18 times 36. And put a point at the centroid of the tendons. We have 12. Okay, that's fine. 2 rows, that's fine. Where is the centroid? At the middle. And then measure the distance between the 2 points. This is called eccentricity. And this eccentricity equal 1.167 feet. One more question. Can you tell me what is the pre-stressing force? Do you remember that? FB ultimate, I don't care about this number. This number is nothing for me right now. My concern is the initial pre-stress equal 175, but this is a stress. So how can I convert this stress to a force, to initial pre-stressing force? So this stress 175, the initial pre-stress time, the area for the whole tendons, which is given 1.836. This pre-stress force equal 321.3 kip. Yes, thank you, Brock. Okay, we almost done. We almost done. So right now, we have moment due to the effect of unweight equal 210,937 pound feet. And we have a cross section with a force here equal 321.3 kip with eccentricity equal 14 inch, which is 1.167 feet. Can you go ahead and draw or calculate the stresses? Yes, I can. Due to the effect of moment, we have a stress equal my over I. For the pre-stressing force, we have stress uniform. This one will be tension. This one will be compression. This one will be compression, compression. The force divide area. And due to the effect of eccentricity, we have compression at the bottom, tension at the top, and your stress equal force time eccentricity time y divide I. If you go back to our last meeting, you can find the three cases. I know some of you will ask this question. It's a very good question, and please make sure you can get it. The effect of this pre-stressing force is acting at the bottom. So at the bottom, we have compression. That means at the top, we will have tension. That makes sense? This moment coming from the effect of unweight or effect of external load. What do you think? I believe the external load will make tension at the bottom and compression at the top. So we have tension and compression. So make sure you didn't confuse. And this effect is compression because we assuming this force acting at this centroid. Anyway, to figure out these values, your cross-section properties are not given, but the cross-section is given. We have 18 inch, we have 36 inch. So the area of this cross-section 18 times 36. The moment of inertia I equal parallel 18 times 36 cube over 12. Here is the neutral axis at the centroid. That means the distance y here equal 18 inch and the distance y here equal 18 inch. Y for the bottom and y for the top. So these values, area 18 times 36 equal 648 inch square. Parallel times 36 cube over 12 will be 69,984 inch to power 4. So we have I, we have Y, and we have moment. But please be careful, because this moment in pound feet, and everything in the section properties in inch. So make sure your units are consistent. So M will be 210,937 times 12 to be pound inch, time Y 18 inch, divide I 69,984. So the two stresses will be equal. $651. How much this force? This force equal 321.3 kips. So I will multiply it by 1,000. Divided by area 648. This stress equal 495. For this one, the force equal 321.3 times 1,000 to be in pound. Time eccentricity 14 inch. Please make sure everything in inch. Y 18 inch. I, we calculated I. So 321.3 times 1,000 time eccentricity 14 inch time Y 18 inch divide I 69,984. This stress will be 1,156. 1,156. Finally, can you tell me what is the final stress? Okay, we have here compression, both of them will be added, 651 plus 495 minus 1,156. This one is the biggest one, so we will have tension equal 10 psi. At the bottom, we have tension, we have compression. So the two compression will be added, 495 plus 1,156 minus 651. The final will be compression equal 1,000 psi. Here is the final stress. Any question? I don't care about the signs, positive or negative. My concern is, please tell me, is it compression or is it tension? Will both forces always equal? Which forces? Brock, regarding your question, which forces? This one equal to this one because you have a cross section give you this y distance equal to this y distance. You are lucky because your cross section looks like a rectangle. So the centroid and the neutral axis at the mid height. So the distance at the bottom equals the distance at the top. So your stress at the bottom equals the stress at the top. But if you go back to the previous example, last meeting, we have something different. Something like this. So this distance is not equal to this distance. So at this time, you will get two different values. This value will be different than this value. So it depends on the cross section. If you got a distance to the top equals the distance to the bottom, the two values are equal. It's number. M times Y divide I. I, moment of inertia for the cross section, is constant. Moment is the applied moment, is constant. So which one is a variable? Y. If the Y distance for the top equals the Y distance for the bottom, both of them must be equal. Okay? This question is very important. How to figure out the final stress? Deflection. Just to let you know, deflection due to the effect of the given load, dead load, plus live load, which is uniform distributed load, the deflection will be downward. How much? I'm sorry, 5 WL to power 4 divide 384 EI. Guys, do you remember what was the value of E? If you go back to the first week in this course, equal 75,000 square root for F prime C. I can tell you what is the value of E concrete. Do you remember that? Anyway, so just to keep in your mind, the deflection due to the effect of external load is downward deflection. How much? This one. By the way, W equal dead load plus live load. We don't have factor, just surface load. If you need to figure out the deflection due to dead load only, okay, W equal dead load only. If you would like to consider the deflection for live load only, W equal live load only. If you would like to consider the deflection for both of them, dead load and the live load, W equal dead load plus live load. Live is easy. The same expression, 5 WL to power 4 divide 384 EI. If you would like to get the deflection for dead load only, okay, W equal dead load. That's it. If you would like to consider live load only, okay, W equal live load only. If you would like to consider the deflection for both of them at the same time, okay, W equal dead load plus live load. We don't use factor 1.2 or 1.6 for deflection. If this beam under the effect of external post tension, we have initial camber, upward deflection. This one was downward deflection. This one will be camber or upward deflection. How much for this deflection? It depends on what is the shape of the, or what is the profile of the tendon. Straight tendon, you can calculate the deflection by this expression. P is the pre-stress force, F. E1 eccentricity, L squared divide 8 EI. If the profile of the tendon looks like trapezoid or trapezoidal shape, like this, the upward deflection will be using this expression. Because the profile is different, so we have two eccentricity, one at the midspan and one at the end. Two eccentricity, E1, E2. If the profile of the tendon looks like a parabola, we have a different expression. But in our course, most 99% of the problem will be straight tendon. So this expression will be used mostly. By the way, the modulus of elasticity E of concrete, you can get it by ACI. Do you remember that? E concrete equal 75,000 square root F prime C. The moment of inertia is calculated for the concrete cross-section based on the shape of the cross-section, rectangular, parallel, time perpendicular cube over 12. Superposition can be used. What you mean by superposition? I mean, you will calculate the deflection due to the effect of load, dead load or live load or both of them, up, downward, and then alone, and then calculate deflection due to pre-stress. This one is upward, this one is downward. This one is alone, this one is alone. That means delta final deflection will be this one, which is downward, plus this one, which is upward, and you need to tell me the final deflection, is it upward or downward? So which one is bigger? This is the meaning of superposition. Superposition means I'm gonna calculate deflection due to weight, due to live load alone, and deflection due to the effect of pre-stressing alone, and then finally I can add them together and see which one is bigger. This is the meaning of superposition. Okay, let's do this example. We have a pre-stressed concrete beam with a span 30 feet with cross-section 20 times 12. The dead and the live load are indicated. We have dead load equal 0.5. We have live load equal 0.8. Pre-stressing tendon have an area of 5.9 inches square. Okay. Ultimate stress, FP ultimate. This information is nothing for me until this moment. I don't care about FP ultimate. My concern is what is the initial pre-stress force and what is the final pre-stress force. I'm sorry, the initial pre-stress and the final pre-stress. Calculate the center line deflection and the midspan just after release and after the final pre-stress is reached. I forget to mention something here. And I covered it last meeting, and I would like to repeat it. Guys, do you, just after construction, 1 second after construction, the beam under the effect of initial pre-stress force and the bridge or the building did not be used by anybody. So we have dead load only. Under surface load, 1 year, 1 month, 5 years later, the beam will be under the effect of F final. Guys, do you remember what is the difference between the initial pre-stress force and the final pre-stress force? What is in between? Do you remember that? I need one word. I need one word. Guys, do you remember? What is the difference between the initial pre-stress force just after construction and the final pre-stress force under surface load? Do you remember that? Not time, not deformation, not shortening, not, I need one word. You guys answered me the same question and the same answer last meeting. And I told you I need one word. One word. Losses. Thank you, Brock. Losses. Losses will include what you said. What you said. Losses will include what you said. Everything. Everything. Explain the difference between the first situation and the final situation. So we have losses between the two situations. Anyway, but under the surface load, the bridge under using. So we have dead load and we have live load. That makes sense? So this problem asked to figure out the deflection just after release, just after construction, and after the effect of pre-stress force, the final pre-stress force. So we have two situations. The first one, just after release. So we have dead load only, and we have initial pre-stress force. That makes sense? Dead load only, how much? 0.5 plus. The problem did not say anything related to the unweight of this beam. So I need to include it. 12 divide 12. 20 divide 12. Time 1. Time 150. All of them divide 1000. Why? Because the given dead load in kib. So I need to divide this number by 1000 to be in kib. The final value for the dead load will be 0.75 kib per foot. The initial pre-stress force equal the area of the tendons 5.9 times the initial pre-stress stress 180. So 5.9 times 180 equal 1062 kibs. Guys, can you tell me what is the deflection D2 dead load, which is downward, equal 5 WL to power 4 divide 384 EI. By the way, F prime C is missed in this problem, equal 5000 PSI. So E concrete equal 75,000 square root F prime C. This value will be 30.5 KSI. Moment of inertia for this cross section equal 12 times 20 cube over 12. This one will be 8,000. So the final value for this deflection equal 5. What is the value of W? if you would like to consider the deflection for dead load only, okay, go ahead and equate W equal dead load only. So your value for W will be 0.75. L 30 to power 4 divide 384 times E 40 30.5 time inertia I 8000. If you get a value, your value will be wrong. Do you know why? You know why? This weight kept per foot. This length foot. This E kept per inch square. This I inch to power 4. Your units are not consistent. Okay, I agree with you, everything in kib. That's fine. But not everything in inch or even in foot. We have some in foot and some in inch. So you need to keep your units consistent. So this 30 will be multiplied by 12 to be in inch. This one kib divide foot. So I will divide this one by 12 to be in inch. Now I can get a final answer. Your final value will be 0.424 inch down. The only problem, the only issue to use this expression to make your units consistent. Please be careful about units. Thank you, Burak. Then, your profile or the profile for this beam is straight. If the problem didn't say anything related to the profile, that means we assume it's a straight. So the deflection equal F the pre-stressing force initial time eccentricity time L square divide 8 EI. This expression. Okay, go ahead and substitute. The initial pre-stressing force 1062 kib. Eccentricity. Guys, this time, can you figure out the eccentricity between the location of the tendon and the centroid? Can you do it this time? Thank you, Alan. Yes, it's 6. Guys, I believe this distance, the remaining distance will be 4, because 4 plus 16 equal 20. The distance between this centroid to the bottom is 10. The distance between the tendon and the bottom is 4. That means the eccentricity equals 6 inch. So eccentricity equals 6. The length of the beam 30. Square. Divide 8 times E 40. 30.5 I 8000. Please make sure your units are consistent. I don't think so. So, because this one in kib, that's fine. This one in inch. This one in feet. This one in kib and divide inch square. This one in inch to power 4. Looks like everything in kib. That's fine. But we have some in feet and some in inch. I need to keep everything in inch. So I need to multiply 30 by 12. So the final value will be 3.2 inch upward. Okay, the problem did not ask to calculate deflection due to dead load alone and the deflection due to pre-stressing alone. We need delta final. So 0.424 down plus 3.2 up. I believe the final deflection will be 2.78 up inch. Just after release, just after construction of pre-stressing, the beam will be cambered up by 2.78 inch. Any question so far? Looks good. Okay. Let's do under surface load. Guys, everything will be changed. Everything. Really? Yeah. Let's see. First of all, your W equal dead load plus live load. Both of them should be considered. So we have dead load 0.75. You need to add the value of the live load 0.8. So the W used for deflection will be 1.55 kb per foot. Your deflection due to load equal 5 WL to power 4 divide 384 EI will be 5 times 1.55 times 30 to power 4 divide 384 times 40 30.5 times I 8000. One more time, make sure your units are consistent. So I will divide this one by 12. I will multiply this one by 12 to figure out the final deflection. Point 876 inch down. For tendons, please go ahead and figure out the value of F. I'm sorry, you figured it out before. F, no. This F was the initial pre-stress force. I used the initial pre-stress, 180. We have final pre-stress after losses. So we need to multiply 140 by this area. So we have another F, 140 times 5.9 equal 826 kb. Your deflection due to pre-stress equal, do you remember that one? FEL square divide 8 EI. So the F 826, eccentricity is the same. 6. L 30 times 12 square 8 E 40 30.5 I 8000. Everything is good. Go ahead and get a number. This one will be 2.5 inch upward. So the final deflection equal 0.876 down plus 2.4 inch up. So the final deflection will be 1.61 inch up. I don't care about the final one is up or down, is safe or unsafe. It's not my point right now. My point is to figure out the final deflection for this beam under the effect of the dead load and live load. That makes sense? Any question? Looks good. Looks like it's nothing, just you are following some steps. So until this moment, we cover two parts. The first part, I can give you a beam with pre-stressing force, and I'm asking to figure out the final stress at the two fibers, at the top and at the bottom. So you need to construct the three shapes with numbers at the top and the bottom, top and bottom, top and bottom, and tell me the final stress. The second part, I will give you a beam, a pre-stressed beam with given load, or probably you can calculate the Unweight of the beam to tell me what is the final deflection, and make sure which deflection I'm looking for. Is it deflection just after release, or deflection, final deflection under the surface load? Because we have a big difference. Just after release, we have Fi without losses. We have dead load only, including the Unweight of the beam. But after losses under surface load, your W or the load will be dead and alive, both of them. And the tendon will lose some forces. So we have F final after considering losses. So make sure you are reading the problem carefully. One more part will be covered next meeting. What is the ultimate design of a cross-section or a pre-stressed cross-section? It's a piece of cake. We covered this before. It will be very easy, nothing new except how to calculate FBS.